So we're probably talking about 900 years old spruce tree here. This is a Sitka spruce. And well, we are now located in the Sitka spruce forest type. It runs in a narrow strip along the Pacific Northwest coast. It starts up in Haines in southern Alaska and then runs all the way down through the northern California. And the Sitka spruce is sort of strip is also on the outer coast of the redwoods. The redwoods can't tolerate that salt spray we talked about earlier this morning. So there's actually a little bit of Sitka spruce forest that runs on the very coast there. The other thing you can always, spruces are always, when you look at the bark, it flakes off like sort of potato chips. Okay? And spruce is a very uniform genus that's found in a circumpolar distribution. So there's lots of spruce in Europe and Asia that are different species than we have here. But the largest spruce and trees are definitely found here in the Pacific Northwest. Okay? And so we'll take a look at how this works. You can hear the winter wren that is singing there. All right, so and we'll keep walking up here. Shallow roots. Shallow roots.
Shallow roots. I guess I'm gonna keep recording just in case.
You just started?
Yeah.
So the growth of trees here is really, they grow very fast. In other words, they put on a lot of biomass. But eventually they all end their life when they get to that 900 or 1,000 years. And in this case here, you can see that the top is blown off. And that's typically a sign of white rot, where they tend to snap. If they got blue rot, which sort of rots the roots that tend to tip over. But the point here is that now we have a snag there. How long is that going to stick around, right? It takes about 400 years for that to completely rot. So we're talking about that a tree from it starts as a seedling to it's completely gone again is about 1,300 years. That's a very long time, right? These dead snags and the logs on the forest floor are really critical components for a lot of wildlife species, and we'll talk a little bit more about that later. Right? There's a new Sitka spruce coming up there. See the difference in the bark on the hemlock compared to the spruce? It's kind of sort of finely grooved. If you see one that's deeply grooved, then it's a Douglas fir. I'll show you one of those. A tree there with sort of much more deeply grooved bark. There's some over here. Those are the Douglas fir. Now, what does that tell us? Well, it tells us that there had to be a fire, probably about 400 or 500 years ago, because they can only regenerate after a fire. Okay, so there hasn't been. Watch out! There's somebody coming. Since they can only regenerate under fire, there must have been a patch of fire here, because we actually got a number of, and they look to be about the same age. Both Sitka spruce and western hemlock and the western red cedar can generate in shade. In other words, they can sprout. However, imagine that the seed falls in here. That's a lot of competition, right? So they will very likely never make it. But they can make it on top of logs, okay? Because then they're elevated and out of the competition. So most of the trees, except for the Douglas fir, starts on what we call a nurse log. So the log is nursing along the new tree. So they often are found in a row, right? Because they're all on the same log. And so I want you to look at that as we walk here in a little bit.
Well, yeah, you've got something growing right out of that one. You've got a tree growing right out of this log right here, so.
Yep. Yeah. There'll be some better examples.
Yes.
The other thing you need to look at is, so when we start talking about oak growth, one other thing I want you to look at the branches way up. They're all filled with a thick layer of moss. And that moss is hundreds of years old in terms of, and so there's actually soil underneath there. Those are good platforms for a little seabird called marble murrelet. Most seabirds, they usually nest on cliffs along the coast. Well, there's a lot of competition for that. So there's a lot of other bird species that want to be there. So the marble murrelet decided that it was going to nest on the branches of oak growth trees within about 50 miles of the coast to get away from the competition. And that was a great idea until we showed up with a chainsaw. Then that strategy was not good anymore. Okay? They are not very good at reproducing. They lay one egg. Then the parents will incubate that egg, and once that's incubated, they fly back out to the coast. Early in the morning, they will capture, both the male and the female will capture some fish. They'll fly in real rapidly, feed the chick, and go back out and come back the next day. Which means that the chick is left to itself. So it's susceptible to predation. If the ledge is not big enough, they fall off. And so they're reproductive, and that's why they are on the endangered species list. So, and when they come in incredibly rapidly. Just as the sun comes up. It's almost still twilight as they come in. Feed the chick and out they go. And the reason for going in at twilight is that hopefully predators will not see them fly in and out, right? Because that's a dead giveaway of where the chick is. So, all right, let's you move up. Watch out, there are some people coming there as well.
Kind of going through the logs, do they eventually just...
Yeah, as they start to rot,
Okay.
and that takes a while, and so sometimes, what the roots will do is they'll grow around, right? We'll let these guys pass. No problem. No problem. So the question was, when these trees start to grow on the log, when do they grow through the log? They really don't, because remember it takes it 400 years to rot. So most of the roots go around, and that's why you got these big buttressed trees that they got this big butt on them. Okay? I just want you to note here that there's been a lot of elk browse, that a lot of the twigs have been sort of nibbled on. So we talk about, we are clearly in an unmanaged forest. It's old growth. And as we were driving in, you saw a lot of managed timber stands, right? They were typically dark in there, and they were all the same age, right? All the trees are planted at the same time, so they become all the same age. Let's give them a little room there to pass by. So here we have a forest that is consisting of trees of all sorts of ages, all the way from seedlings that started this spring to trees that are 800 years old, right? So we have a multi-age stand. It's much more open. There's a lot growing on the forest floor here, right? That means that if you're an elk and a deer, this is a good place to be. When it snows, those managed stands are really good for avoiding snow on the forest floor, but there's nothing to eat. Here, these big guys will redistribute some of the snow, and there will be patches around them close to where they can actually get browse at heavy snowfall. Right? So that's really critical that there's this mixture. So the million-dollar question then becomes, when does a forest become old growth? A lot of people are hung up on time, 200 years, 250, 300 years. I like better to look at the way that the forest sort of functions. And there's a couple of things that you can look at. One of the things is that if you took a tree away in some of those managed stands or opened it up, that gap that would be created would be closed by the branches of the neighboring trees, because there's nothing from the forest floor, right? If I remove any of these big guys, they will be replaced with trees that are already established, the smaller ones, these that are all sorts of ages, right? That's a much better definition, because imagine that if you are at higher latitude or you are at higher elevation, it takes a longer time to get to the old growth, right? But the other beautiful thing about that definition is it also works in a eucalyptus forest. It also works in a hardwood forest. So it's a nice universal definition that can be used in many settings. So that really is sort of a good overall definition. If we narrow it in here to the conifers, when would we start characterize a tree as old growth? And typically we would do that once the morphology of the crown changes. So look at that young tree there. It grows nice and perfectly, very symmetrical, right? And in a very orderly sort of Christmas tree-like fashion. If you start looking at some of these older ones, there's not that symmetry that's lost. The branches are starting to go in all sorts of directions, filling in the gaps, and there's no symmetry to them anymore. Okay? The second part that happens is we start getting those moss-covered branches. Okay? And that change in morphology and the moss takes about 200 years here at low elevation. If you go up higher, it may take longer. Okay? If you go up to northern Vancouver Island, it's probably 250. If you go down to the redwoods, you can probably get it done at 150. Okay? But that's the sort of the test to look for when you're looking at an individual tree rather than the entire forest. So we can scale that old growth definition from an individual tree to a forest, which is pretty neat. Right?
With the Sitka spruce, does that have good fire resistance like the...
No, Sitka spruce, if you have a fire, it has very thin bark, it dies quickly. Hemlock, same thing. The only fire-resistant tree we have here is the Douglas fir. Okay? Now, once we go to the east side, that changes. Okay? But the Douglas fir, once it gets to be really thick, you can put a torch on the bark for a couple of hours and nothing will happen to the tree. Because it has thick bark and there's a fire resistance compounds in the bark that makes it so it is hard to catch fire. Really, really hard. So, yeah. And so, since part of the fire resistance is thick bark, that means that the older the tree gets, the more resistant it gets because the bark gets thicker, right? As they get bigger. So, some of the trees that we are looking at earlier on probably have a bark that's about this thick. And if you can't burn, then that's good insulation. Cool? You need to come, watch out, there are some people that want to go by there, guys. So you need to look at this cut here and look at how wide the wings are in the very beginning of its lifespan. And then as you look out, then they get to be really, really, really tight. And then all of a sudden, they get wider again. That means that the neighbor died and the competition disappeared. So as the neighbor tips over, more light, more nutrients, now I grow fast again. And then, but you should also think about, yeah, these may be thick here, but think about, even though that is 1 millimeter, but it's so much around and so way up there. So these trees actually grow faster and faster. They put on more biomass every single year. Last night, did you hear anything hit your tent? All night long, right? There were needles that were hitting the tent, right? So that's a constant recycling process. Watch out, there are some more people that want to get by there. And so that's another critical component, that there's all this sort of stuff that comes off every year. Right? So we put on biomass, but we lose biomass as well. If you're looking at the amount that we have above ground, what we are not seeing is what's below ground. And that's about 4 times as much. So there's about 4 times as much carbon below the ground as there is above the ground. This is some of the fastest growing forests. This would be a perfect place to store a lot of carbon if we decide that we will want to pay for that. This is the place to grow forests that stores carbon, right? So yeah, take a look at this here. You can sort of take a quick look at that. So obviously the log that it started on is gone, right? And now you have this buttress. And as this grows, this is only probably maybe 250 years old. It's a young little guy. And as this gets bigger, this gap sort of disappears and fills in, right? This is the potato chip. All spruce trees have potato chip. All the species, regardless of where you are in the northern hemisphere. But they vary in size. They all have shallow roots, because they're all adapted to either permafrost or wet areas or rocky environments. So they all have shallow roots. You'll never find any spruce with a taproot. That's not going to happen. Spruce cone in there. It's a woodpecker. Okay, sticks it in there and then it picks out the seeds. And I'm sure if we look down there, there's a lot more. So this is they come back there day after day and do the same thing. There are other places where you'll find where the Douglas squirrel will eat cones, and there will be a pile of scales, because it's a really, really good spot, and they're used over and over and over again. When the inhabitant dies, or for some reason, somebody will move in within a day. And so some of those piles are over 100 years old. So as soon as a tree dies, there's a lot of other critters that wants to get a piece of the action. And most of those are wasps. There are wood wasps, and then there are beetles. And they usually the larvae can take up to 12 years to develop in this. Eating sawdust, that's a pretty lean diet, okay? You're not going to grow very fast. And so once this starts to get rotten, that's when the woodpeckers start coming in and opening up. And the round ones are usually the smaller woodpeckers, but the more sort of rectangular ones, That's the pileated woodpecker. That's our largest woodpecker that we have. It always forages in square holes, and so it's a good sign that they're here. Right? Those large woodpeckers is one of those indicator species of a healthy forest, because so every year they build a new nest. So they excavate a new cavity. They don't use the same. That means that for other birds that needs a cavity, all of a sudden there's a vacant sign, right, for sale.
Yeah.
So somebody else will move in and use that. So these primary cavity nesters are really important for secondary cavity nesters because they can't.
Why do they move? Do they move after they breed, or?
So they have one batch of young in there and then they move out, because otherwise they don't want diseases to carry over. If they get lice or anything like that, you don't want to have anything, and that's very typical. Mason bees, for instance, will only use the same hole once, and then they'll move out the next year. And so it makes sense in terms from a strategy, right? Which, opposed to eagles, for instance, they use the same nest year after year, and it gets bigger and bigger. So the eagle nest, if they've been used for 4 or 5 years, it can weigh up to 1/2 metric ton because they keep building on it. And then eventually it gets to the point where the tree, may break off and the whole thing come crashing down, and they're going to start over. And actually eagles, when they first breeding for the very first season, obviously it's the smallest nest. They're usually not very successful because the young fall out of the nest because it's not very big, particularly if there's a couple. So after a couple of years, then they get more successful because now that they got a bigger platform to move around on. It used to be, it splits all the way up to the top there. Right?
These are the Sitka spruce.
That one there's in there, growing in the shade of this alder here. Right? So look at the shoots, how small they are. They grow very, very slowly because they are so much in the shade, right? But come August, end of August, early September, the alder is going to lose its leaves, and then they can start photosynthesizing and store some of that for next spring, and then they can photosynthesize a little bit in the spring before this comes out, and that's how they hang in there. That's why they're called shade tolerant. They just hang in there until eventually, because they will get bigger than the alder, right? So eventually they will escape the canopy of the alder, and then they start growing fast again. But it can take a very long time to get to that level. But if you're patient and you adapt it to it, you can do that. Hemlock does the same thing. Cedar does the same thing. They started on the same nurse log, and because of the Sitka spruce shading this guy a little bit, it grew a lot slower. Right? Well, he's still here after a couple hundred years, so he's not a total loser. He's just coming in second, right? The losers would be the one that are, right? Different place. We have a lot of moss here, but that's sort of general because of the humidity. And this is a big leaf maple. But all of a sudden we have a little bit of a grassland here, right? So why do we have a grassland here and we had a forest floor community in here? Well, the reason is that we have lots of elk, and elk likes to graze. And so this little meadow is actually maintained by the elk by coming in here grazing every year. So any kind of little seedling that may have started gets nibbled off. And so we get very low recruitment of trees. And so this is the other thing that we need to sort of think about is as we walk through it, think about how much structural complexity we have. Remember we talked about structural complexity translates into more niches, which translates into more species, right? So if you are dependent on that you can only live in a snag, in a cavity, way high up, like swifts, well, then you're going to have old dead trees, right? So you're only going to get that here. You're not going to get that in the managed forest. Okay? If you want big cavities to nest in, like spotted owls do, you need big trees and you need big dead trees, typically, right? So bats love old trees because they can get in and during the day behind the bark, or they need a cavity for the females to have their young. You're not going to get that in a young sort of managed forest there. That's just not going to happen. So as we are walking through here, the old floodplain here, watch out for elk. There's a lot of people here today, so that might not be possible, but you never know. Right. So this is a big lichen. It fell down from the top of the trees when the wind blows. So why would this be important? Well, it's important because the lichens have a very high nitrogen content, so it's a preferred food by elk and deer, particularly in the winter. Think about this being covered in snow. If you have a nice little wind and all of this stuff blows off the canopies, all of a sudden there's a subsidy for some good food, right? And so this is primarily utilized by deer in the winter. Further north, woodland caribou and really depends on this. Now the thing is that you're not going to get lichens growing on a young tree. Again, you've got to have old trees. They don't start growing on trees until they get about 100, 150 years old. So if our rotation of trees is 60 years, this is not happening. So, watch out, there's some people coming by. There's blue earlier on. So this has been, the hole here within the national park has been a good reference point for how those rivers behave when we have not interfered with them, right? Because we got a normal forest here that has been untouched. That means that the wood that comes in there is really, really big, and you saw where it ends up out on the beach this morning, right? And so you can see here there's a log jam that's been buried, right? It's holding a lot of sediment, and we're building an island. So the wood helps making the rivers more complex. It stores sediment, and they run a little bit slower. But if they run a little bit slower, that means there are less erosion of sediment at the bottom, and that's where the salmon has their eggs. In other words, that's where they lay their eggs, so they don't get scoured out in the winter, right? So that's really a critical component. As the river rises during really sort of the rainy season, there's a lot, if the water gets really high, this is where you're going to hang as a juvenile, because you're going to be able to be there all winter long, right? Otherwise you get flushed out. It's like putting a little goldfish in a toilet bowl and flush it, right? It's not, it can't hang on, right? Because the water moves too fast. So they're going to be able to hide in those little crevices in there during high flow. So that's where. You can also see that there's a very distinct riparian zone over there of alder, and there's some, in other words, it is a deciduous forest. That's very important for our tropical or neotropical or migratory birds. It's full of songbirds. Right? It's very productive when it comes to songbirds. And notice that most of this is willow and alder, as we talked about when we were on the Skagit. Right? So, cool. And get a sort of a visual of what that looks like. So this is sort of zooming out a little bit and looking at an old-growth forest at a distance, how sort of coarse the canopy is. And I want you to take a look when we leave and look out the window and look at our managed forest lands, right? How uniform it is. It looks like almost like a lawn, right? That's not the case here. So the big challenge is that if you're a forest landowner your valuable asset is primarily growing trees and selling the trunks. The most valuable asset here for wildlife is the dead trees and the deciduous components at the forest floor. So you can see that if we're going to manage for wildlife and we're going to manage for timber, something's going to have to give, right? We can't have those dark sort of uniform stands because then it has no wildlife values whatsoever. So that's what we're trying to get at by having these clumps of leaf trees and leaving the riparian zones and all of that stuff so we can accommodate the wildlife species, right? Now there's obviously a cost to that. But remember, all of these critters that are in here are also performing ecosystem services, right? So that's important to think about. And that's white sturgeon. We have very little green sturgeon left. They're on the endangered species list because they like estuaries, and we've modified most estuaries. So this is an old riverbed. It's dry, so it's a meander scar, right? See this vandalism here? Is it vandalism? Is it teenagers behaving badly? Well, how do we get the trees ripped up like that? So this is the elk when they want to get the velvet off their antlers just before rutting season. They try to rub it off, and so they use the trees here. Well, elk are big and rough, and so they end up sort of debarking them a little bit. So this is all antler rubbing from elk. The big ones here, deer does the same thing, but it's typically not as dramatic as this one here. It doesn't kill the tree the first time, but if they continue, it's, you know.
びっくりしたそれは。
怖い。
いきなり僕の後ろにいてた。
So we talked about that there's a lot of biomass here, but how much? How does this stack up on a global scale? But according to Jerry Franklin, which is a forest ecologist down at the UW, that's worked extensively out here, he